In this lecture, we are going to discuss relationship between cross power and cross correlation function. This is similar to the relationship between power spectral density and autocorrelation function. So the statement of this relation is given below. Okay, so the cross power spectral density, as I said in the previous lecture, is denoted by Sxy of omega, and this is equal to time average of cross correlation function, that is limit t goes to infinity 1 over 2t integral minus t2 plus t or xy of t comma t plus tau. This is a time average, right? Times dt, and this time average cross correlation function, you take Fourier transform of this e to the minus j omega tau and d tau Fourier transform. So this is a relationship between cross power spectral density Sxy of omega and cross correlation function Rxy of t comma t plus tau. By the way, this is comma. Okay. Now let us prove this property. The development of the proof consists of using the transforms of the truncated process. Like as I said, we have two random process x of t and y of t, and in the random process x of t contains there are many sample functions like this, and the sample function goes up to infinity. Let me call the sample functions x1 of t, x2 of t, and so on and so forth. So therefore the collection of waveforms is called the random process capital X of t. Similarly, in random process y of t also you have many noisy waveforms, random waveforms. So again the collection of random waveforms are called random process. Let me call these waveforms y1 of t, y2 of t, and so on and so forth. This also may go up to infinity. Now since the waveform exists from minus infinity to plus infinity, I cannot see the waveform at one go. So what do I do is I truncate the waveform from minus t to plus t. So let me take any one waveform, and that waveform is denoted by x of t, and the duration or existence of this waveform is minus infinity to plus infinity. Let me truncate this waveform. The truncated waveform is denoted by capital suffix t, xt of t, and this t indicates truncated, truncated, truncated version of x of t. So this truncated version of x of t is defined as x of t minus t less than or equal to t less than or equal to capital T and 0 elsewhere. Similarly, for this random process, you take any one sample function, you denote it by y of t, and the truncated version is yt of t. Same definition. It's y of t and it exists from minus t and 0 elsewhere. So this is the definition. And as I said in the previous lecture, these two waveforms are truncated version of your original waveform. Therefore, let us assume that it doesn't have any discontinuity, and it's absolutely integrable. That means it is Fourier transformable. So x suffix t of t, if you take Fourier transform, you will get xt of omega, and then yt of t, you take Fourier transform, you get yt of omega. So the Fourier transform xt of omega is equal to, you take xt of t, multiply with the e to the minus j omega t dt, and the limit is minus infinity to plus infinity. By the way, let me call this is equation number 1, and this one equation 2. Then yt of omega is equal to integral of minus infinity plus infinity. Then I am using different running variable. Let me call yt1 e to the minus j omega t1 dt1. So let me say this is 3. Now we need to find out the complex conjugate of xt of omega, but because that is the one that which you are going to use it. So in this you take complex conjugate, xt conjugate of omega. So this is xt of omega, sorry, this is t, right? Xt of t e to the minus j omega t dt, and whole complex conjugate. So the conjugate comes here, conjugate comes here, and the conjugate comes here. So this is xt of t conjugate e to the minus j omega t conjugate dt conjugate, and this is a real quantity, and this is also real, but this becomes e to the j omega t. So integral of xt of t e to the plus j omega t times dt, and the limit is minus infinity to plus infinity. Here x suffix t of t is a real ensemble member from the random process x of t. Therefore we used the thing like xt star of t equal to xt of t. This is the thing we used here, assumption. Now let's find this quantity. xt conjugate of omega times yt of omega is equal to multiplication of these two. So this is since the signal is minus t to plus t, maybe I'll write down this minus infinity to plus infinity, xt of t e to the plus j omega t times dt minus infinity to plus infinity, yt of t1 e to the minus j omega t1 dt1. Since the signal exists from minus t to plus t, I can put the limit minus t to plus t. I'm sorry, I can put no, there is subscript is not needed, x of t, because you are capturing that x of t from minus t to plus t, e to the j omega t t dt integral of y of t e to the minus j omega t1 dt1. This is also t1, and the limit is minus t to plus t. Now the cross power density spectrum sxy of omega is given by sxy of omega is equal to limit t goes to infinity 1 by 2 t expected value of xt conjugate of omega and yt of omega. This is a result that we proved in the last lecture, so please go through this lecture if you have any difficulty. So substitute this xt star of omega and yt of omega in this expression. Limit t goes to infinity 1 over t 2t integral of expectation of xt conjugate of omega is minus t2 plus t x of t e to the j omega t dt integral of y of t t1 e to the minus j omega t1 times dt1, the limit is minus t2 plus t. Now combine these two integral, limit t goes to infinity 1 over 2t, expectation of double integral, and the limits are minus t2 plus t, minus t2 plus t, then x of t y of t e to the j omega t times e to the minus j omega t. You can combine these two guys and rearrange e to the minus j omega times t1 minus t times dt and dt1. Now since expectation is a linear operator, you can take it inside the integration. So limit t tends to infinity 1 over 2t minus t2 plus t minus t2 plus t, the limits are, then expectation of x of t and y of t times e to the minus j omega times t1 minus t dt times dt1. Now as I said in the previous lecture, this doesn't have any meaning because it is a sample function, right? So expectation is an operator that is defined only for random variables. So therefore what you do, instead of taking one simple function, sample function, take a process, random process x of t and sample at a time instant t1, t, let's say t, you will get a random variable. Similarly, you take y of t and sample the process at a time instant t1, let's say this is suffix t1, and here also suffix t1, that's it. So instead of y of t1, small y of t1, you put a capital Y of t1. This is the random variable. So the expectation is defined on the random variables, not on the sample function or time waveform. Time waveform you cannot find or you cannot get any value, because as I said, expectation is e of x equal to integral of x times fx of x into dx, right? For this waveform, how do you substitute here? You cannot substitute. So this you have to substitute a value for that. Okay, for random variables, you sample the random process, then only you can apply this formula. Okay, so therefore the above expression modifies as limit t goes to infinity 1 over 2t double integral, and the limits are minus t2 plus t, then this is expectation of x of t times y of t1 multiply by e to the j omega minus j omega times t1 minus t dt times dt1. Now don't you see, this is the cross correlation, this is y, right? Cross correlation of x and y. So or x y of t comma t1. So limit t goes to infinity 1 over 2t double integral, this is or x y of t comma t1 times e to the minus j omega t1 minus t dt dt1. So on the left hand side you have Fourier power spectral density S x y of omega. Now take inverse Fourier transform on both sides of the equation. This, let me call this equation number 5. I don't know which equation is 4. Maybe, yeah, let me call this is equation number 4. Then, yeah, 3 is there and 2 is different. Fine. So, take the inverse Fourier transform both sides of equation 5. Okay. So, inverse Fourier transform, 1 over 2 pi integral of sxy of omega e to the j omega, let me call the random variable tau in order to avoid the confusion, d omega, and the limit is minus infinity to plus infinity. So here also 1 over 2 pi integral minus infinity to plus infinity, limit t tends to infinity 1 over 2t, and then double integral or xy of t comma t1 e to the minus j omega times t1 minus t dt dt1, and this whole thing multiply by e to the j omega tau d omega. Now let me rearrange this, rearrange on the right hand side. This is limit t tends to infinity 1 over 2t double integral minus t to plus t, the limits are r xy of t comma t1, then you bring this 1 over 2 pi here and this entire, then integral, the limit is minus infinity to plus infinity, and combine this exponent and this exponent. So e power j omega times tau minus t1 plus t, and put a d omega first, then dt1 and dt. Now look at this integration, this one. Let me use different color. So this one. Okay, look at this integral. This integral can be written as follows. I mean, this is an inverse Fourier transform of e to the j omega of minus t1 plus t. Okay, if you take an inverse Fourier transform of this guy, you'll get this one. It's very fairly simple proof. The same thing I did in the last lecture also. Anyway, if you want, I can work out for a while. So there is small digression. Recall from your signals and systems. Like if you take x of t, then you'll get x of omega, or I can put a dummy variable. After all, t is a dummy variable, right? It's a running variable. So x of t, you'll get a x of omega. Then x of tau minus some time shift in the time domain is equal to e to the j omega t1 times x of omega. Then x of tau minus t1 plus t. Then in the frequency domain, say if you have a minus sign, here also minus sign will come. So this minus reflects here. Okay, so e to the minus j omega t1 times e to the plus j omega t times x of omega, that is e to the j omega t minus t1 times x of omega, or minus t1 plus t times x of omega. Okay, that means what? The Fourier transform of this guy is going to be this one. If you take inverse Fourier transform of this, then you'll come back here. Okay, therefore the inverse Before that, one more point I want to just stress here. Now instead of, we know that del of t, if you take Fourier transform, you will get 1, right? So del of tau, you can take Fourier transform, again you will get 1. Then del of tau minus t1, you will get Fourier transform of that 1 times e to the minus j omega t1. Del of tau minus t1 plus t, if you take Fourier transform, then it is e to the j omega minus t1 plus t, right? Therefore, the inverse Fourier transform of this one is this guy, right? So this one, if you take inverse Fourier transform, then this is going to be del of tau minus t1 plus t. So this is limit t goes to infinity 1 over 2t double integral minus t2 plus t minus t2 plus t or xy of t comma t1 times, that is del of tau minus t1 plus t times dt1 and dt. Now, by symmetry property of impulse function, del of minus t is, or I can say del of t equal to del of minus t, okay, or either way you can write, no problem, okay. So therefore del of tau minus t1 plus t, this guy, is equal to del of, just negate the index, minus tau plus t1 minus t. So I can write this as t1 minus t minus tau. Therefore the above integral becomes, or equation becomes, t goes to infinity 1 over 2t double integral or xy of t comma, this is comma actually, don't confuse it, comma, t comma t1 times del of t1 minus t minus tau dt1 and dt. Now use the following property again from impulse function. If we have a function phi of t, multiply by del of t and dt, and the limit is minus infinity to plus infinity, use this property, which is equal to phi of 0 integral of phi of t times del of t minus t naught times dt, which is phi of t naught. See, the integration is with respect to t, and this variable also t, and this also t, and here also t, right? Similarly, if you look at here, this is t, t1, let me use some other color, and this variable also t1. So this t1 is replaced by this parameter. So in this, if you have like this, phi of t times del of t minus t naught and dt is equal to phi of t naught. How? You are doing integration with respect to t, and the parameter is t. So this t is replaced by what? T naught. Similarly, in this integration, let's say, minus t2 plus t, this also minus t2 plus t. So if you consider this integration, in this, you are integrating with respect to t1, and the delta function is del of t1 minus t minus tau, and the autocorrelation function is, or cross correlation function is, r xy of t comma t1. Therefore, this t1 you replace by t plus tau. Here if you have minus sign, then here you have plus sign. This is a property of your impulse functions, please recall. So therefore the above integral becomes limit t goes to infinity 1 over 2t. Now one integration will go away. This is going to be the cross correlation Rxy of t comma, the t1 is replaced by t plus tau and dt. Okay, so this is the expression finally you will end up, and this no is valid in the range from this one is valid in the range from minus t less than t plus tau less than capital T. Okay, this equation is valid only in this interval. But this condition can be ignored as t goes to infinity in the limit. If you take the limit, then that will go away. In the left hand side we have integral of sxy of omega times e to the j omega tau d omega. There is a constant scaling factor minus infinity to plus infinity. This is equal to limit t goes to infinity 1 over 2t integral of Rxy of t comma t plus tau dt. Now in the left hand side you can see it is the inverse Fourier transform of what? The cross spectral density Sxy of omega between x and y. In the right hand side, if you notice, what you are doing essentially is you are taking the cross correlation function Rxy of t comma t plus tau and integrate over a period minus t to plus t, let's say, with respect to t. And what is the duration? Minus t to plus t. So the interval length is 2t. If you divide by 2t, then you are finding the time average of cross correlation function. And once if you let t to go to infinity, then you are finding the time average over from minus infinity to plus infinity. So therefore the right hand side indicates, this indicates time average of cross correlation function. Cross correlation function. So again, if you take Fourier transform on both sides, this inverse Fourier transform will go away. Therefore, Sxy of omega is equal to Fourier transform of time average. Time average is denoted by the letter A of cross correlation function t comma t plus tau. By the way, this is comma. Fourier transform. Okay, so this you can substitute if you want. So it should be noted from the above equation that given the cross power spectrum, this is given, you cannot find the cross correlation function in general. Okay, so from the given cross power spectrum, the cross correlation function in general cannot be recovered. Okay, cannot in general be recovered. Only its time average can be determined. So if this is given, only you can find out time average. You cannot find the cross correlation function. Somebody gives you the cross power spectral density. With that, you cannot find what is what xy of Rxy of t comma t plus tau. This you cannot find out cross correlation. But what you can find is, you can find a time average of this is given from that you can find time average of Rxy of t comma t plus tau, that is cross correlation. So time average of cross correlation can be found from the given cross power spectral density, that is average average thing, no, time average you can get it, but you cannot get exactly the cross correlation function. But there is a special case occurs when the process is WSS stationary, then yes, you can find the cross correlation function also. Okay, so whenever you have jointly WSS process, jointly WSS, what we mean by WSS, wide sense stationary random process. In that case, the cross correlation function becomes t comma t plus tau becomes Rxy, sorry, this is y, right? I'm sorry, Rxy of tau. Therefore, whenever you have jointly wide sense stationary random process, that means what? X of t is wide sense stationary. When jointly wide sense stationary means x of t is wide sense stationary, y of t is wide sense stationary, and x of t and y of t together wide sense stationary. So in that case, your cross correlation function is independent of the time at which you do the sampling. It depends only the time difference between the two samples, x of t and y of t plus tau. So in that case, the time average becomes statistical average, that is A of Rxy of t comma t plus tau will be equal to the ensemble average Rxy of tau. So this is time average of cross correlation function, and this is ensemble average. Don't call it ensemble, it is ensemble average, or you can say statistical average. You take the average across the ensemble. Okay. So in that case, I know cross correlation function can be found from Sxx of y. Therefore, jointly WSS process given Sxy of omega, you can find what? The cross correlation function Rxy of tau. If it is jointly WSS, yes, there is a possibility you can get this cross correlation function. If it is not WSS process, no, you cannot find out the cross correlation function, but you can find out the time average of cross correlation function. Okay, so that's a relationship between cross correlation function and cross power spectral density function Sxy of omega. This is Sxy of omega. So at this point, let me stop. Thank you very much.